So I'm starting my today's session, and the class will not be taken in MS Team because I'm not comfortable. So Zoom will be continued. The other people are joining. So by this time, I'm writing one statement, one theorem from the book. The theorem, which we already discussed in the last class. I discussed it in my way, but the proper statement of the theorem wasn't written. I said that we study the equivalence relation. It's because the equivalence relation gives you or helps you to divide the entire set into different segments. Okay. And I cited the example of rational numbers, where I told you that you consider any fraction, and that fraction will constitute a class because you can get many rational numbers which are equivalent to that particular fraction. And the important result which we studied, that no such equivalence class is ever empty. And if an element belongs to an equivalence class generated by some other element, then the class represented by the element and class represented by that element, they will be actually same. So that means if half constitute the class in the rational number, then any fraction, say for example 2/4, will constitute a class which will be same as the class of half. And I also told that if you can get two classes, either the two classes are disjoint or they are equal. And the lastly, which I asked you to prove by yourself, is that take all possible classes generated by elements, and you take the union of that class, those classes. This union may be an infinite union or maybe a finite union. If you do so, you will get the entire set from which the elements which generated the classes were taken. Okay. Now I ask all of you, you keep listening to me and write your university roll number in the chat box so that I can save it for attendance. Now the theorem which I'm writing over goes like this. The statement of the theorem is let rho be an equivalence relation or a set A. Okay, then P is equal to class A, where A belonging to the set capital A is a partition of capital A. Okay, so this theorem means that suppose this is my set capital A, then if I consider this class A is actually constitute a partition, one partition. Another element to choose from capital A, say for the element, let us consider the element to be small b, then class B constitute another partition. So, and for example, if I consider another element from set A, say small c, then class C constitute another partition, and so on. So we can name those partitions to be, suppose this partition to be P1, this partition to be P2, this partition to be P3, so that P1 union P2 union P3 and so on gives you capital A. This has been written in this particular theorem. Okay. Now, another interesting property in yesterday I talked about, let me save your chat just a minute. Yesterday I talked about three different relations. One relation was one particular property was reflexive type of relation. Another relation I considered was symmetric relation. And another relation I considered was transitive relation. Okay. Now, apart from this, and I also told that if all these relations are satisfied, all these properties are satisfied by a relation, then such a relation, if all are satisfied, such a relation is called equivalence relation. Equivalence relation. And as it is clear from the above theorem that equivalence relation always constitute equivalence classes. If you have equivalence relation, then you can design an equivalence class. If you have an equivalence class corresponding to that, an equivalence relation always exists. Apart from these three different relations, another interesting relation is sometimes studied, and that relation is known as, let me write its name. It is called antisymmetric relation. Antisymmetric relation. So today I am going to first define what we mean by antisymmetric relation. The definition goes like this. A relation R on a set A is said to be antisymmetric if for all A comma B belonging to A, whenever A is related to B and B is related to A, then A is equal to B. Whenever I write any definition or any theorem, if I write the statement, you can see that when I copy the statement of the theorem, or if I copy the definition, I always look at the book. Because sometimes what happens that if I miss one word, by mistake, if I miss one word, say for example, I forgot to mention this word for all, then there will be trouble, because the mathematics you are learning right now is abstract. And every word written over here is very important, very significant. So I do not take the, courage to write the definition by memorizing it. Okay, because I am teaching you. So that's why I'm copying the definition from the book or statement of the theorem, so that no error should be present over there. Your job is similar. Whenever you are going to study this sort of thing, whenever I say this is the definition, you just try to memorize each and every word written in the definition as it is. Say for example, I have underlined a few words in this particular statement, if for all, and then I'm underlining this word whenever and the word then. So be careful about these words. Okay. Now, what are the examples? I'm going to show you one or two examples for this. First of all, let us begin with the example which I considered in my last class. So my example was, I considered the set capital A. The set consisted of these four elements, and suppose I am considering a relation. And you know relation, those who were not present in the last class, if rho is a relation, defined on A, it means rho is a subset of A cross A. Okay, so rho is actually a set, collection of ordered pairs. It's a binary relation. We are considering the rho to be like this, say 1, 1, and 1, 2, 2, 3, okay, 3, 4, and 4, 4. We want to check whether this particular relation is antisymmetric or not. Now this, I'm putting a star over here because this is a atypical problem, and you have to understand and you have to be very careful about this particular problem and what I'm going to tell you. Now you see 1, 1, 1, 2, 2, 3, 3, 4, 4, 4. Okay. Now you see, look at this definition of antisymmetric relation. In this relation, what did I write? That if whenever these two hold together, that is A is related to B and B is related to A. For the sake of your, I want to recapitulate one thing, that when I write ARB, it actually means that the ordered pair AB belongs to the relation R. Okay, remember I talked about it in the last class. So you see that this particular pair 1, 1, this particular pair 4, 4, they are actually satisfying these properties. Why? Because if I consider, since here A equal to 1 and B is also equal to 1, so 1, 1 belongs to rho. So you can consider this one to be A and this one to be B, and 1, 1 also belongs to rho. You can consider now this to be B and this to be A, and together they imply that A equal to B, which is obviously equal to 1. Similar is the case with 4, 4, 4. Okay. Now, what about these three items, 1, 2, 2, 3, and 3, 4? It is mentioned that when ARB and BRA both hold together, then they must imply that A equals to B. But here you carefully observe that 1, 2 is present. Here 1, 2 is present. So we actually must have an element like 2, 1. Okay, so if 1, 2 and 2, 1 are present, then suppose, for example, let me write in another page. Suppose in the element, in the relation 1, 2 is, along with 1, 2, 2, 1 is also present. Suppose it is present. What will happen then? Suppose it is present. Can we write that A equals to B? Answer is no. Why? Because 1 is not equal to 2. Okay, suppose 2, 1 was present over here. So and we want to check the property that AB and BA belonging to the relation implies A equal to B. So suppose 1, 2 and 2, 1 both are present. We cannot write 1 equal to 2, A equals to B, because 1 is not equal to 2. And therefore, rho will not be antisymmetric. Rho will not be antisymmetric. Isn't it? Now you see, here in this particular case, 2, 1 is not present. So this possibility of not being antisymmetric is not occurring. For 2, 3, 3, 2 is not present. Its twin is not present. So not being antisymmetric is not occurring. For 3, 4, its twin 4, 3 is not present. So not being antisymmetric is not occurring. And therefore, I can say that with respect to all these pairs, rho is antisymmetric we use the word vacuously. This term is very important. So I have put a star mark over there. And the logic has been written here. Okay, so in such a case, we call that this relation is antisymmetric vacuously. Okay, this is all about mathematical logic, and we have mathematical logic in our unit 2 of the unit, I think unit 2 of the syllabus. Then we shall study about the relevant, about the intricacies and relevance of mathematical logic in this discrete mathematics course curriculum. So I have given one example that rho is antisymmetric. Okay, now let me give you another example. So for example, question number, we can consider this question to be question number 1. And now I'm considering the second one to be question number 2. Okay, so let us take the question from the book. Let us consider the set R. The set R, look at the symbol, it is the set of real numbers, and define a relation on R by rho is equal to AB belonging to R cross R, A minus B, such that A minus B is less than or equal to 0. Okay. Now let us consider the properties whether this relation rho is let me put this as a problem. Okay, check whether rho is reflexive, antisymmetric, symmetric, and transitive. We shall check all these properties with respect to the given relation. Okay, so let us check these one by one. Solution. First of all, we are choosing a pair AA from rho. Let AA and we see that A minus A is less than or equal to 0, as A minus A is equal to 0, and 0 can be written as 0 is equal to 0. 0 is equal to 0. Okay, where A comma A belongs to R cross R. Okay, so this implies that A comma A belongs to rho. This implies A rho A is related to A. This implies rho is reflexive. Okay, this is point number 1. So we can name it as A. Number B, antisymmetric. Let us check this property. Okay, let A comma B and B comma A belong to row. Okay, where A, B, and B, A are elements of R cross R. Since they belong to row both, this implies that A minus B less than or equal to 0 and B minus A less than or equal to 0. This implies A minus A less than or equal to, sorry, A less than or equal to B and B less than or equal to A. This implies A is equal to B from the property of real numbers, from the property of real numbers. Okay, so what we see that when A, B and B, A both belonging to row, it implies that A equal to B. Therefore, row is antisymmetric. Row is antisymmetric. Okay. With your permission, I'm going to the next page. Okay, if I do not do so, then you can click a picture of that if you are not able to write it quickly. Otherwise, the time will be killed, and my class will be, I will not be able to cover many things in the class. So we have got that row is antisymmetric. You can do it by yourself. Now let us check the property of symmetricity. Let A, B belonging to R cross R be an element of row. This means that A minus B less than or equal to 0. Now, this implies that whenever we write B minus A, then the inequality gets changed. Okay, and this implies consequently that B comma A doesn't belong to row, because for to be an element of row, it must be less than or equal to 0. So therefore, this gives us that row is not symmetric. It is antisymmetric, but it is not symmetric. Okay. Number D, let us choose A comma B and B comma C from R cross R, which belong to row. This implies that A minus B is less than or equal to 0 and B minus C is less than or equal to 0. Now we can add them together. A minus B plus B minus C is less than or equal to 0 plus 0. This implies A minus B plus B minus C is less than or equal to 0. And this implies A minus C is less than or equal to 0, because B minus B equal to 0 by the property of integers. And therefore, A and C, the ordered pair AC, belongs to row. So whenever AB, BC belonging to row, then AC belonging to row, this gives us that row is transitive. Row is transitive. So we have got row is reflexive, transitive, but not symmetric. Okay, which implies that rho is not an equivalence, relation. Okay, and on the other hand, this is my conclusion. This is my one of the conclusions. Conclusion number one. My conclusion number two is that rho is reflexive, antisymmetric, and transitive. So question is, what do we get then? Okay, what do we get then? So let me give you another definition on the next page, and then I'm going to fill the blank over here. So this is a question, what do we call the relation rho then? So the now next definition, again, you have to be very careful because I'm going to write a definition now. Okay, so definition goes like this. A relation R on a set capital A is said to be partial order on A, okay, if R is reflexive, antisymmetric, and transitive. Okay, so in the previous example, my rho is a part, the relation rho is a partial order relation. Okay, and the second part of the definition goes like this. A partial order relation on a set A, on a set capital A, is usually denoted by this symbol. It is not, in this case, it is not lesser than or equal to symbol. If it is a matter of finding partial order, then often we use this symbol, or you can use any symbol, because in the previous case, rho was the relation which we considered and which came out to be partial order. The important part is the set A, the set capital A, along with the partial order, defined on it is called a partial ordered set or POSET. Partial ordered set or POSET. So in the previous example, in this example, with respect to the previous example, with respect to the previous example, we call the set of real numbers along with the relation rho, which is partial order relation is to be a POSET. To be a POSET. Okay. You can take another example. I can take another example. You can try it at home. It's very easy. The question goes like this. Let capital A be any non-empty set. Capital A be any non-empty set. And PA is the power set of A. Power set of A. Power set constitute all possible subsets of A. Power set of a set is the collection of all possible subsets of the set. Okay. Now you see, we define a relation which we usually call a subset relation. It is a subset relation. We call subset. You know very well. We define a relation this on PA, the power set of A, where any two sets X and Y taken from PA satisfy one of the following. Either X is subset of Y or X is not subset of Y. Okay. Can we consider PA along with the relation subset to be a POSET? This is the question. Or is this a partial order relation? So I am leaving this particular problem for you to check by yourself. Got it? So we have got 4 types of relations in this particular section. 2 relations were discussed in the last class. They were reflexive relations, symmetric relation, and transitive relation. And if a particular relation satisfies all these properties, reflexivity, symmetricity, transitivity, then the relation becomes an equivalence relation. On the other hand, there is another relation which goes by the name of antisymmetric relation. So we have studied here that if a particular relation satisfies the property of reflexivity, antisymmetricity, transitivity, then this relation is a partial order relation. The 2 types of relations, important relations we have designed. One is equivalence relation, one is partial order relation. If you have an equivalence relation, then with respect to these equivalence relations, equivalence classes can be designed. These equivalence classes can be considered as partitions. You would combine all the partitions, you get the entire set under consideration. Or if you have an equivalence class, you can always design an equivalence relation with respect to that equivalence class. Keep this thing on one part, on the left side of yours. Okay. Another idea which you have got from here is that if we have a partial order relation, the set under consideration along with that partial order give you a different kind of set which is called POSET. Sometimes it is also called partial ordered set. So on one hand, you have equivalence class and equivalence relation. On the other hand, you have partial order relation and POSET. Okay, so try to figure out these things in your brain in this particular manner, and do not be haphazard in learning these things. I shall, since time is running out, I shall conclude my today's first session by giving you this definition. This definition goes like this: a POSET A comma rho, where obviously you know that rho is partial order relation, is called linearly ordered set. Linearly ordered set or chain if for all A comma B belonging to A, either A row B or B row A must hold. That is, either A comma B belongs to row or B comma A belongs to row must hold. If such a scenario occur, this partial ordered set or POSET is called linearly ordered set. I'm stopping right now. We shall meet in the next session of today's class.